start with just one brief thing because I've noticed some of you guys who have done the CAN project, it seems like you maybe misunderstood one part of it, sort of a central part of it, which is, okay, so we've got a CAN, right? And it's some unknown radius and some unknown height, okay, whatever those are. But the volume needs to be what? 16 fluid ounces, okay, just and or whatever that is in milliliters. What was it, like 473 or something? Okay, so that's whatever it is, right? But then the other thing is, well, what is the volume of a cylinder? Right, the area of the base, which is pi r squared, times the height, which is, of course, h, okay? And we want this to equal a specific number. I'll just put 473 milliliters, but whatever units, like you can work in metric units, you can work in imperial units. It doesn't really matter as long as you pick a unit set and you're consistent. Other work in metric units, they're better, right? And I guess one other thing while we're on the subject, what is a milliliter, by the way? Does anybody happen to know? Hmm? Like, okay, so milliliter is a liquid measure, right? What is that in terms of a linear measure? So this is equal to a cubic centimeter, yeah. Okay. And then I'm sure you could look up whatever the equivalent conversion factor is for the imperial units. Of course, this is one of the things that makes the metric system so nice, is that this is true, right? One thing is equal to one thing. There's no funky number, right? And so sometimes actually, I'll write 1 cc here. Sometimes you actually see cc instead of cubic centimeter, particularly in the medical field, right? Like if you have to take a liquid medication, or you have to either like to drink or to inject, then often the dosages are given in cc's rather than milliliters. Huh? Um, I think that's just the way the medical industry does it. Yeah, I'm not entirely sure why that's uh, why they use cc instead of ml when they're obviously equivalent units. Um, that's a good question. So if anybody runs into Dr. Roberts or Dr. Douglas or something, or Nurse Amadon, maybe we could ask them. Maybe they have a good answer for that. But anyway, same unit is just a different abbreviation for it. So if you see CC out there in the wild, then this is what it is. And right, okay. So that said, right, the volume is supposed to be constant. Okay, and what is it that we're trying to optimize here? Not quite. We're trying to optimize the cost. Okay, and there's a difference between the cost and the surface area, because we'll assume that the sides of the can cost $1 per unit area. So it's $1 per square meter. That doesn't mean the actual can side costs a dollar. It's going to be obviously some very small fraction of a dollar, because the side of the can is not an entire square meter, okay, material. But then the top could be $1 per unit, $2 per unit, or $3 per unit, okay? And so what I would do is suppose that it's a dollars per unit, or some other letter. The letter doesn't matter, okay? And what's critical about that, right, is if you minimize the surface area, then you are assuming that the top and the bottom cost the same amount per unit area as the sides. And if you do that, you're basically getting the answer that goes with the $1 situation. Okay. But what happens then if it's a $2 situation? Do you just say, oh, well, then I have the same shape and then the top and the bottom cost twice as much now? No. Okay. Why? If you have carte blanche to design this can however you want, and the top and the bottom cost more, and you can make the can tall and skinny or, shorter and fatter. If you can make it any shape you want, and you know that the top and the bottom cost A units, whereas the sides cost $1 units, then what are you going to do? The shape of the can itself will be different. Okay, and so let's just kind of use our heads here. If the cost of let's say that the sides cost $1 per unit area, and the top and the bottom cost $1 million per unit area, are you going to make a can that looks like this? Hell no. Are you going to make a can that looks like this? It's going to be closer to that. You're actually would, under those conditions, produce a can that's like a pencil width, but the like really, really tall. Okay, now obviously that's a little ridiculous, right? I'm exaggerating here for sake of explanation, right? But the actual can shape that's optimal changes if the costs are different. It's still a can, right? And it still has whatever the volume is, but you can't just say, okay, let me find the optimal for $1 and then compute the cost, assuming that the top and the bottom of that same can are $2 per unit area. Okay, does that make sense? Yeah? Okay, maybe to put this another way, let's go back to one of the other optimizations problems that we did that was much simpler, okay, when we were fencing in an area. Okay, so we did several problems like that. We fenced in an area where we were going to fence all four sides. Okay, and let's say that we had 1,000 meters of fence with which to do that. What was our optimum shape? Huh? Assuming that it was a rectangular shape to begin with, right? It turned out it was a square, right? And it would be, 250 or whatever it is on either side. Okay. Well, then we reworked the problem, assuming that we did it first where it had to be a rectangle where we were fencing all four sides. And it turned out that the optimal shape was a square. Okay. But then we did another version where we were building it up against a barn so that we only had to fence 3 out of the 4 sides, but we still got a rectangle out of it. And what was the optimal shape there? Was it a square? No. It was a 2 by 1 or 1 by 2, depending on which way you measure it, right? It was a genuine rectangle, non-square. Okay, so the constraint changed, and the shape therefore changed to reflect that. And that same thing is going to be true with the can. Okay, does that make sense? Right, that's maybe a subtle point, but it's like the central premise of the entire project, is that what shape your optimal can will be will depend on this number, right? So you're going to find the optimal in terms of the number A and then plug in 1, 2, or 3 for it, not beforehand, okay? Uh, Equivalently, right, this is the difference between minimizing cost versus surface area. If you're trying to minimize surface area, that's the $1 situation where there's no cost difference between the top and the sides. But is cost the same thing as surface area? No, they're very, very deeply related. They're almost the same thing, but they're not quite. Okay. Yet another way to put that is we did another optimization problem where, like, there was a dude that he wanted to get to a campsite that was on the other side of the river, right? And we could walk, we could swim, and we could walk at certain rates. And the and whatever those rates were. Okay, and what were we trying to optimize there? Time, not distance, right? If I want to minimize the distance between 2 points, what do I do? Yeah, just go in a straight line from one point to the other. Done, right? That's easy. Okay, but if I want to minimize time, that's not necessarily the same as distance because the rates at which you can travel might be different. Now, let's assume that like with that swimming and walking problem, if you could swim at exactly the same rate you could walk, what would be the optimal solution? The straight line. Okay, but of course the premise of the problem is that you can't swim as fast as you can walk, right? That just makes sense. Okay, and as such, you aren't going to take a straight line, but sort of a bent, two line segments that come together at some point. Okay, does that make sense? Okay, let me give you a real world example of this, as if going swimming and walking to your campsite's not real world enough. Okay, and so let's go to the bastion of all knowledge of Western civilization. Mm-hmm. Okay, so how many of you guys? It'd be great if the keyboard would come up. Huh? Okay, you know what? There we go. Okay. How many of you guys have ever heard of Snell's law before? Okay, so this is actually a real world example of the walking versus swimming kind of thing. Okay, so if you have, for example, light, okay, light travels at a particular speed, right? In air, it's one thing. In vacuum, it's maximum. Okay, in water, it travels about 2/3 as fast as it does in vacuum. Okay, and there's a really neat consequence of that, which I'll talk about in a second. All right, so let's suppose that we have a light beam that's going to go through an interface between two materials. Okay, for example, air and water. Say I've got a glass of water on my table, okay, or a bowl or something, right? The water doesn't go as fast in, or sorry, the light doesn't go as fast in the water as it does in air. Okay, all right, so let's suppose that I have a beam of light, like a laser or something, and I'm shining it at the surface of the water, okay? And let's imagine that I went in a straight line to the side of the cup. Would the laser actually hit there? No. What happens to the light? It refracts slightly when it hits the interface medium. Okay, this is why when you look at, like, let's say you have a cup of water and you've got a penny, you look at the penny and you're like, okay, that's cool, and then you drop it in the water, it looks a little bit different. Yeah, because the light has been refracted by the water. Okay, another way to sort of explain why this is happening, right, is that the speed at which the light beam can travel changes. Okay, and what light is trying to do is to minimize the time it takes to get from one place to another. Okay, and that isn't a straight line. Now it turns out, okay, and this is what Snell's law is so you notice how there's two angles there, right? We come in at one angle, let's call that theta 1, and the beam refracts to some new angle, theta 2. Okay, if let's say that it was water in both compartments, what would be true about theta 1 and theta 2? They'd be the exact same thing, okay, because there's no refraction if you go from water to water, you're still in water, okay? But if there is a medium change, then that angle is going to change from what it was to some other value, okay? And the relationship between those is this. The sine of those angles, the ratio of those sines, is actually equal to the ratio of the velocities, okay? Which is interesting, right? So what would happen if the velocity of in air is bigger than that in water? So what is this ratio right here? Like, what kind of number is it? Smaller than 1, right? That under what circumstances is this ratio flat equal to 1? Only if you're not changing from one medium to another. Okay, meaning it's the same speed of light in both media. Okay, all right. If this ratio is less than 1, and then what has to be true about angle 2 versus angle 1? It has to be smaller to make the sine of it smaller. Okay, which, does that make sense looking at the picture? Yes. Okay. So, believe it or not, you remember the problem that we did with the campsite, right? We could have actually solved it with Snell's law. And believe it or not, it makes the math way less messy, okay? Because when we did it, we had all those nasty square roots and it was a big giant mess. Yeah? Well, there's no square roots there. It's just some trig. I like trig. Yeah? Okay, so this is where I need to have like my little meme cards, right? Because there's the one with like the guy in the turtleneck sweater with like the, right? You guys know what I'm talking about, right? Oh, okay. We're gonna go from Wikipedia to Jiffy. This guy, right? Yeah, that guy. Yeah. Okay, I need to put that on a thing. All right, let me go back to Wikipedia though, because there's one other interesting thing I'm going to digress about. Okay, which is I just said that um, oops, that the speed of light is slower in water, right? Okay, in vacuum, can you have a particle moving faster than the speed of light? Not unless you watch Star Trek. No, you cannot, right? Well, not either not yet or never, right? Okay, that's the speed limit in the universe is the speed of light. Okay, in water, the speed of light is like what, 2/3 of what it is in vacuum. Is it possible for a particle to go faster than that in water? Yes. Okay, so it's possible to exceed the speed of light, but you can't ever do that in a vacuum. You can only do it in a medium where the speed of light is actually lower. Okay, so do you guys, you're not going faster than the speed of light in vacuum than the speed of light in water. Okay, this actually can happen, and the place that it happens, amongst other things, is in nuclear reactors. Okay, so let's look at this picture. You see that weird blue glow, right? Looks kind of scary, like, oh, that's a nuclear reactor. I don't want to touch it or be anywhere near the vicinity. Maybe I'll go to the other side of the planet, kind of thing. Okay, that is called Cherenkov radiation. This occurs when electrons or other, subatomic particles in the course of nuclear reaction are traveling through the water faster than light can go in that medium. Okay, what happens is they're going through and they produce a shock wave that gives off photons at a particular wavelength, which is sort of this bluish color. And what you're seeing is the photons emitted by this shock wave. Okay. Yep. Okay. And yeah, because obviously if we did this in air, the speed of light in air is, still slower than the speed of light in vacuum, but just a lot closer to it. Water, like if we did this in oil, for example, I'm sure it would be even lower. But we probably wouldn't be able to see these photons because oil is, real thick and opaque. Okay. Um, now, that's a visual example of this, but the same sort of thing happens. Has anybody ever lived near like an Air Force base or something where planes are going faster than the speed of sound? All right, what happens if a plane goes faster than the speed of sound? It does, okay? And what do you hear when that happens? You hear a boom, right? What you're hearing there is a shock wave of, because the plane is moving through the air faster than the air can basically get out of the way. Okay, this is sort of the same kind of phenomenon. Something is going through the medium too fast, and there's a shock wave because of it. It's just that this one you see visually rather than hearing auditorily. Well, there's no stuff in a vacuum, right? So there's no material for there to be a shock wave to form, right? It's vacuum by definition, right? So, yeah. Yes. Okay. So that would be more so, would be kind of like, let's say you had just a bonfire and you look up, okay, the hot air, right? The density of that air is different, and it kind of, the light like looks funny, right? It's the same thing. Basically, it's just air is not, the air outside is not some perfectly uniform substance. Huh? No, you're not ripping a portal open to another dimension or anything like in Rick and Morty, okay? Um, it's just kind of a visual effect, right? And it's because the light going through the air, that air is not a uniform medium. And so it's going to be refracting and bouncing and twisting and doing all kinds of, I mean, it's the same. Why is the sky blue? Yeah, light refracting through water, basically there's water in the air. Light refracts through this, and we see that as a blue shifting wavelength. Yeah, so it looks blue. Um, how much ocean do you see outside? River, ocean. Yeah, okay, totally not the same thing. Huh? Yeah, and it better have sharks with freaking laser beams. Okay, so, all right. Anyway, let's get back to today's lesson. Okay. So anyway, there's your hashtag Goodrich Hall moment of the day. Okay. So let's return to what we were doing last time. Okay. Which was, we were looking at the first fundamental theorem of calculus. And what I want to do is sort of develop this and the idea into the second fundamental theorem. Okay. Let's take some examples of things that we did. Okay. We did this. Okay. Last time. Let's suppose that I have a function that I'm going to define as being an accumulated area. And just for convenience, let me pick 0 for the bottom, just for giggles. Okay. What were we trying to answer last time? We were trying to answer not what f was, but what f prime was. What does it turn out in this case to be? Just turned out to be x. Okay. Why? That was the fundamental theorem. Yes? Okay. Let's do another one. Say we had this one. Okay, this was the parabola one that we did. So let's actually back up a moment and remember how we approach this. Okay, if I have a parabola and I want to find the area from 0 to x that's underneath of it, what I could instead do, oops, is think about the area of that rectangle is what? X times x squared, right? okay, if it's x units along the base and x squared units along the top. Why is it x squared units along the top, by the way? Well, what's my function, right? What gives me this parabola? T squared, right, or x squared, okay? So that's the area of that entire rectangle. But I don't want the area of the entire rectangle. I want the area of this green piece, okay? I don't know what that is, but I do know the area of that orange piece, okay? And in particular, I know the area of the orange piece because it's 4/3 of that triangle. Okay, so let's use our heads here. It's going to be x cubed minus something, okay? X cubed is the entire rectangle, and I'm about to subtract out the the orange part that I don't want to leave the green part. Okay, what is the orange part? We said last time by Archimedes, it's 4/3 of that triangle. Well, what is the triangle's area? Okay, x cubed, careful, divided by 2. And then I need to multiply that by 4/3 to get the entire orange area. Okay, do you guys buy that? All right, what do we get if we do this subtraction? No, sorry, I don't. It's I never actually highlighted the triangle. It's this part. Yeah. So the x squared, or sorry, x cubed over 3 is the blue triangle. Okay, and then the orange kind of wedge-looking shape was what we actually needed to subtract, and we knew that it was 4/3 of the triangle because of that result of Archimedes that I talked about last time. Okay. All right. So all we did here was find the area of that sort of green wedge by taking the total and subtracting out the crap we don't want. Good? And when we do all that subtraction, what do we get? Okay. Now, what is the derivative of this function? Okay, so that's g of x. What is g prime of x? Yes, x squared, which is exactly this. Okay, so if I had said, all right, I've got this area function, which I defined as capital G of x, right, whatever it is, and I say, all right, I don't need to know what that function is to know what its derivative is. Okay, that's sort of the beauty of that version of the fundamental theorem is did I ever actually need to know, like in the first problem, did I ever actually figure out what big F was equal to? No, I never found a formula for it. Okay, but I do know what its derivative is. Okay, now in the second one, we went ahead and did figure out what formula for G, and what do we get? 1/3 x cubed. What's its derivative? X squared, which is exactly what would we have gotten if we had plugged x into the thing that's inside the integral. Hmm. This is interesting. I don't have much of a beard to really like cogitate on, but what's the relationship between x squared and 1/3 x cubed? Yeah, all right. It depends on which way you say it. Okay, so there's two correct answers to that question. So what's the relationship between x squared and 1/3 x cubed? One of them is the derivative of the other, or the antiderivative of the other. Okay, so which way is it? X squared is the derivative of 1/3 x cubed, and therefore 1/3 x cubed is an antiderivative of x squared. Okay, now why did I say and? Because there's that annoying plus c business. Okay, which we'll have to deal with later. So it turns out then that there's a very deep relationship between this idea of integrating. Okay, so let's think of it this way. Over in the left corner of the room, is the idea of doing an integral, okay, which has to do with areas, right? Over in the right corner of the room is the concept of antiderivatives. Is there any, like, if you just walked in the room and over there was all this stuff about area and accumulating area, and over there was this idea of antiderivatives, and you look down and you say, oh, areas, yeah, that we talked about that in math class, and antiderivatives, yeah, that's something we talked about in calculus. Is there any, like, obvious, like, you wouldn't look at that and say, oh, those must immediately be related to each other? No, right? But it turns out that they are. And that is the second fundamental theorem of calculus. Okay, is that this idea of accumulating areas and this idea of antiderivative actually are linked in some way. Okay, so let's go back quite a bit. What was our notation for antiderivatives? Yeah. Don't those notations look pretty damn similar to each other? Okay, in particular, what's common? The squiggly, right? The weird looking S shape. Okay, now how many of you guys thought up until this point that that was just a gigantic coincidence? It's not, right? The reason that we use this symbol for antiderivatives is because we started using this symbol for area, and then we found out that, oh, this thing actually has something to do with this idea of antiderivative. So why don't we just use this symbol without the decorations at the top and the bottom to mean the idea of an antiderivative? They're related, so why not just reuse the same notation? The lack of the top and bottom is what gives you the plus C. You don't have to have a plus C, exactly. Okay. Okay, so, wow, they're actually related. Okay, is the sort of miracle discovery, right? And this is why it's called the fundamental theorem of freaking calculus, because these two things are related to each other, even though, like I said, at first glance, you might have no reason whatsoever to suspect that they were, until you start digging into it and working examples like this and saying, this is really interesting, that it turns out that the area somehow relates to the antiderivative of the thing that I'm finding the area under. Right? Brain explosion. That's interesting. Maybe this works for other functions too, right? Okay, because here, basically, what examples have we done? Oh, and while we're on the subject, by the way, what is this? Why is it that? If I go x units here and x units there, what's the area of that triangle? Right, it's a triangle, x squared over 2. Well, x squared over 2, that's an antiderivative of x, isn't it? Right? Okay, now, how do you know that I just haven't cherry-picked two functions for which this happens to work? You don't know that. Yeah, blind trust? I don't know if it's blind trust. I mean, I've been mostly competent this semester. I mean, occasionally I'm pretty incompetent, but like, I'd like to think I actually know my freaking calculus. I've been doing it longer than you punks have been alive, so thank you. Yeah, it was a pretty long time. You know, we had to fight off rabid pterodactyls and cavemen and stuff to get to school, walking uphill both ways in the snow without shoes, and we liked it. And we didn't use calculators because they hadn't been invented yet. Right? Yeah, actually, no. I had my trusty TI-82. That's what they were called back then. We didn't even have 83s or 84 pluses or whatever you punks nowadays have, right? Or things with color screens and high resolution LCD graphics. And Yeah, and Flappy Bird. Yeah. No, we had none of this. Okay. So anyway, it turns out that I'm not fooling you, right? This relationship that we've noticed, stumbled on with these two functions, actually does hold for really any function. Okay, so I haven't hoodwinked you. Okay, so let's kind of change our question a little bit, and let me go over here and say, all right, if I want to find the area between 2 points A and B underneath some function, right? This was the symbol that we used to represent, so let's say I've got some squiggly function there, f of x, and I've got A here and B there. Then this represented that area, okay? With one caveat, what was true about the area? What was true about the integral versus the area? Are they identically the same thing? Can the area be negative? No, but can the integral be negative? Yes. Okay, so the integral is not precisely the concept of area. It's really close to it, and the way that I like to say this is, let's call it net area. Okay, so why net area? So how many of you guys have taken econ of some sort, right? All right, so what's the idea of net revenue or net anything in economics? But with the stuff being taken out, right? So if I want to know what my net revenue is, I've got money coming in, but I've also got money going out the door, right? Okay, so what is my revenue coming in? Well, whatever number that is. Okay, but the net revenue, the net cash flow or whatever, I have to then subtract however much money is going out the door, right? So let's say that I'm getting $1,000 in from my customers, but I have to pay $500 to in wages and materials and production costs. How much money really is coming into my bank account? $500, not 1,000, right? And that this concept makes sense, right? Well, it's the same thing with the integral. The integral is not finding the area, but rather finding the net area. Okay, what areas count negative in our worldview here? No, the integral, the squiggly symbol, right? That concept. Okay, so what areas count negative? If it's below the x-axis. And what areas count positive? Those areas which are above the x-axis. Okay? All right, so second fundamental theorem. Okay, so let's suppose that we've got an antiderivative, fatty f, of the function little f. Okay, and I want to find the area in between two mystery points A and B, whatever they are. Okay, then if you know an antiderivative, all you have to do is evaluate it at the 2 points. Okay, now you guys remember what that little vertical bar meant? It's been a while since we've used it. What did the vertical bar with a number at the top and or bottom mean? Plug that thing in, okay? And if there's a number at the top and at the bottom, the notation means plug in the top, you get something. Plug in the bottom, you get something else, and put a minus sign in between. Okay, so I'm going to plug in the top and subtract what I get when I plug in the bottom. Okay, now that shouldn't look all that weird because we did this a bunch last time when we were looking at those area functions, okay, where the right hand or top thing was the dude that had a plus and we needed to subtract off the one at the bottom. Okay, does that make sense? Okay, so there we go. The key challenge to all of this, though, and this is what makes calculus hard, or this stuff hard, is finding the damn antiderivative in the first place. Okay? If the function little f is something easy, like a polynomial, finding the antiderivative of it is pretty easy. Well, it's not trivial, but it's not rocket science either. Okay? Right? But what about if the function's a little bit more exotic? Well, okay, if you've got a calculator that, but you know, somebody had to program the calculator to know what the heck the antiderivatives are. Okay, which means somebody had to figure it out what they were without a calculator in the first place. Okay, so that's the hard part, is actually finding these antiderivatives. If the function is nice, it's not too bad, but if the function's really nasty, we'll have to use a trick, okay, or a technique, which is called the technique of substitution. That's what we'll talk about on Friday. Okay, so does that idea make sense? Okay, so let's take just a couple of quick examples here. Well, let's actually just redo the problem we just worked, right? So we did that area that was underneath a parabola, right? And we got 1/3 something or other, okay? I'm going to pick just the number 0 and 1 here as two constants, just for sake of example, okay? What should we have gotten if everything we did over here was correct? We should have gotten 1/3, namely what happens if I let x equal 1. Okay, do we buy that? Okay, let's make sure that we do. Well, my first step is, what is an antiderivative of x squared? 1/3 x cubed. Okay, and let me actually just put the plus c here to be pedantic and show you why in this case it doesn't matter. Okay, in general it does, but if we've got an integral where there's numbers at the top and the bottom, you don't need the plus c. I'll illustrate why. Okay, what do I need to do to that? I need to plug in 0 and I need to plug in 1 and I need to subtract. Okay, all right, so I'm going to plug in 1 and I'm going to plug in 0. Oops. And I'm going to subtract. Sound good? Okay, what happens to the c's? They cancel, and this is why you don't need to put them there in the first place, because they're just going to cancel out anyway. Okay, you could put them there, that's technically correct, but again, they're just going to disappear in the end, so why bother from the get-go? Okay, yeah, so this guy and this guy cancel because of the minus that's in between. Do we agree about that? We buy it? We? No? We neither buy nor don't buy it? You buy it. Okay. All right, so what do we get for the rest of it? 1/3, which is what we were expecting from what we did it a minute ago. Okay, just using some geometry, right? So before this point, before we had the second fundamental theorem, the only technique we had to figure out these areas was using our damn head with some geometry. Okay, and how did we figure it out in the case of a linear function? Well, the area was just like a triangle, right? Do we really need calculus to figure that out? No, that's easy. Okay, then I said, all right, let's step it up to a parabola. Do we need calculus to find the area enclosed by a parabola? Well, that's maybe a bit more of a debate, but did we need modern calculus to do it, and why not? What was the key piece of knowledge that allowed us to tackle the parabola case before we had this fundamental theorem business? Well, yeah, but how do I get those areas? Okay, we could have either done the Riemann sum, but that's modern calculus. Okay, how did I do this with not modern calculus? With my ancient arcane knowledge. That 4/3 thing that I got because I've read Archimedes. Right? Okay, and it's worth noting, by the way, would Newton or Simpson, or we haven't mentioned Simpson yet, Riemann was a little later, but would Newton, or I did mention Isaac Barrow, Newton's teacher, right? They were Lucasian professors of mathematics at Cambridge. Okay. Would they have read Archimedes? You bet your ass. In fact, their job duties, they were contractually obligated to lecture on subjects of geometry, which included all the ancients, right? So they would have been intimately familiar with this ancient knowledge too. And that informed in some way their developments in calculus. Okay. Question? No? Okay, so the key is finding the antiderivative. That's the part that can get a little nasty. Okay, and so that's what I want to do basically Friday and maybe a little bit on Monday. We'll polish it off. Okay, is to really talk about when is it easy to find antiderivatives and what do you do if it's not so easy. Okay, all right, let me change the question a little bit and see if you guys can figure this one out. Do you know an antiderivative of that function? Not off the top of your head. I guarantee you do not know one. There is. Okay. There are some functions for which there is not an antiderivative that can be written down. Okay, let me give you an example of one. Nope. Okay. And right. So don't, because it's not the derivative, it's the antiderivative. Right. Nah, it's actually worse than that. Turns out this relates to inverse trig functions. Remember those? Okay. So this integral over here, this antiderivative, not only is it, well, let me throw a minus in front of the x just for giggles. It doesn't actually change much. There is no way to write the answer to that question in terms of what we call elementary functions. Okay, elementary functions are every polynomial, everything that involves the square root, e to the x, the logarithm, all the trig functions, okay, pile all those together and everything you could possibly get by combining them in weird ass ways, all those things are still elementary. Good question. There's a shit ton of things that are not elementary, and this antiderivative is one of them. No, it is a new thing. Okay, so this is what's a little bit freaky. If you take an elementary function, okay, which is like I said, something that got built out of, it could be, take the entire chalkboard of this room to write it down. You can find the derivative of it. Might take you a while, but the derivative of it is also elementary. Proof, we have the chain product and quotient and power and all of those rules. Okay, but it turns out that antiderivatives somehow leave the space of elementary functions into the world of special functions. Experience. Okay, you just have to lock yourself in a room and try really hard. Now, you might say, why would I care about the antiderivative of that function? It turns out that that's related to the bell curve and probability. And that's something that's kind of useful, right? That really sucks that we don't know the antiderivative of it. Okay. Well, okay, we do know what the antiderivative of it is. It's not an elementary function. It's this new thing. Okay. So anyway, we'll continue next time.